So we've got a presentation on how to protect open source with a hardware root of trust and the advantages you get with an FPGA, and about how a lot of this applies to DC-SCM. So as we quickly look at the agenda, what's going to make this different than the 17 or 18 other hardware root of trust presentations you've seen before, right? We all know it's important. We're going to factor in some other information about what community effort we need behind doing some standardization. We know the CSPs and the hyperscalers really led the way on a hardware root of trust, seeding the market several years ago. Also, what advantages does using an FPGA versus an ASIC give you? And at the end, how can we take the advantages that we're applying to a DC-SCM and get the advantages in other platforms as well? One thing that I feel gets lost when we talk about hardware root of trust is the problem statement behind it. You can see here, this comes from NIST, the National Vulnerability Database. These are all of the cited firmware vulnerabilities since 1999 when they started collecting the data. You'll see it starts out really small, and there's a few firmware vulnerabilities. There's a few, and these can apply to BIOS, to BMC, to third-party add-on cards, to stuff coming from silicon vendors, all sorts of things. But you can see around 2014, it starts to spike a little bit. It starts to spike even more in 2017, and then it really climbs. And it looks like it's going down, which is good, but at the same time, this is not an issue that's going away. Now, why did these things happen? Coming from a firmware background, there's a lot of standardization that happened over the past 20 years in firmware. Previously, you'd create very targeted attacks. Now they can be deployed on multiple systems because of the standardization that's put there. And also, firmware engineers are no different than other software engineers. Of course, they might know a little bit more about hardware, but they're not infallible. And we use encryption technologies that are used across the entire industry. So when you are claiming security, these things need constant gardening and update at the same time. So the last little orange part there is just a projection based upon how the fact the year's not over. But you can pull this data yourself. We've linked the source at the bottom there. But again, why firmware now, right? Your system is really built on a chain of trust. And over the past 40, 50 years, a lot of that upper layer right there is where security's been focused. But now, from a platform level, you also need to focus. Firmware runs at a privileged level. So if you're protecting the top 10 floors of your building, but not the basement, the worst they can do is they can cut power, they can destroy the platform, they can do all of these other things. So firmware is really your zero trust start. You've got the power on of the system. You then want to make sure that the firmware there is good and it doesn't have any malware, and it continues up through your hypervisor, your OS layers, any sort of applications, middleware that you're also going to run on top of that. Firmware also won't be able to, if there's any vulnerabilities in it, you're not going to find it with any virus scanners or any modern tools that most people are aware of running at the OS level. It's really a privileged early access execution, or it's running the management of the entire system, so it's running in sideband to you and you don't really have any capabilities. So you want to focus on validating and the boot integrity of that firmware. We won't go into much detail of it, but you also want to attest it. You not only want to make sure it's authentic, but you want to make sure it's the version that you want it to be. We've talked a little bit here about the BIOS and the BMC and their privileged capabilities. Adding the hardware root of trust to this recipe will really create a much more secure platform for the future. And of course, we've got to talk now about your kind of general 3 tenets of what does it mean to protect the firmware. The hardware root of trust, platform, firmware resiliency, whatever you want to call it, it's got the 3 tenets of protect, detect, and recover. So you want to protect the platform firmware from any unauthorized changes. You want to detect when those things happen. And you also want to then recover the firmware to a known good state, which basically gives you a lot of flexibility to develop a lot of this. But choosing the right solution that meets your needs really depends upon, or you need to be aware of which hardware you're going to pick. And my colleague, Munir, will then go into how an FPGA improves it.
Thank you, Zachary, and thank you all for attending this session. My name is Munir Ahmad. I'm from Lattice Semiconductor. So let me take from this slide. So if you look at, there's three tenets, right, on hardware root of trust. One is protection, detection, and recovery. And by the way, this is also you need to think about this way, that before even you allow the system to boot up, you need to have a way to make sure that the firmware that it is booting up from is authenticated. And definitely that could be BIOS, that could be BMC, anything that is the privileged states of the firmware that can really do the harm to a lot of harm to the server. That's what you care about, right? And that's what this protect, detect, and recover comes on, and both in before power up state as well as a power up state. And that's what actually, someone who can control the power can actually hold it, right? We can actually, if you look at the CPLD, all the power sequencing today is done by the CPLD. So it would be an ideal place for the CPLD to actually hold the BIOS, BMC, CPU, everything on reset mode, and then go and authenticate all the firmwares, that whatever firmwares you want to, authenticate it, whatever you think is a privileged firmware, and then allow the firmware to boot on, right? That's the whole idea is. So if I go to the next one, so the PFR basically it's an Intel term, but it came from, if you look at NIST compliance 800-193, NIST doesn't say exactly how we implement that, but PFR basically Intel implementation of the NIST compliance, right? So the PFR is basically is using a hardware-based root of trust. And it's a new approach, I would say that, because it addresses these three big things. It's the protection, detection, and recovery. That means when you boot it up, you try to detect the problem. And if you have any problem, if you see any problem, you have to have an alternate way that you can recover this firmware, right? So that means you're not on the mercy of someone hacked your system and you're out of the service. You are actually you're giving a protection, recovery mechanism to the server vendors that, hey, this is where you can recover, right? So that's one of the things, the PFR tenets. And definitely the protection is, we talked about recovery, we talked about detection. And also you need to weigh a mechanism that anytime somebody wants to snoop up your buses, somebody wants to send an illegal command, it could be I2C, it could be spy commands, you want to make sure that you understand this command is legal or illegal, right? Is it authenticated command or not? Same thing because today everything, is all the firmware update is done through the BMC. You want to understand that any update that has happened is authenticated. So that's what the protection mechanism works today. So what is interesting is if you look at the programmability of FPGA is, this is what is, it has a huge advantage because FPGA can work as your power sequencing algorithm. Plus FPGA can also, if you put an FPGA as a root of trust of the security, because security landscape is very different, right? It's changing all the time. You need something that is programmable, that you can react to the market need, right? So if you have something ASIC based, there is definitely a problem that, it's a hard, it's definitely work good, but who knows that 3 months from now, something like a Spectre meltdown is gonna come. There's no way to predict the future, right? Whereas FPGA, you can actually program, and then you can do this in kind of like a soft protection mechanism that you can actually protect some of the things, right? And I think if you look at FPGA, it's definitely scalable. You can have multiple, it has, it's a parallel processing power. So you don't need to have serial processing. If some of the, if you look at some of the attack vector, it's a single byte command. You need to react within the single byte command. You're talking about few nanoseconds of delay, right? So if you have multiple of these sequential command coming through, then how do you protect it with a single ASICs, right? Because you need a parallel thread looking at multiple places, and you need like 4 or 5 nanoseconds of response time. So that's pretty much, so we are saying that, we need to look at that FPGA as well. And if you look at even NIST 800-193, they are also talking about that this parallelism is needed to protect multiple firmwares. You don't know where the attack is going to come from. And obviously, the nanosecond response that is needed for this as well. So I'm going to talk a little bit about DCSCM, and I think this is what is interesting if you look at why DCSCM come out. So if you look at the server landscape, there's 4 things the server has. You have compute module, you have storage module, you have I/O module, and then you have management module, right? Now, I/O guys, they already come out with modular, right? They have this NIC cards. They don't depend on the CPU generation, right? So motherboard vendor who makes a new CPU, Intel comes with a new CPU, motherboard vendor goes and build a CPU. They don't depend on the data card because it's a modular form factor. Similarly, storage, if you look at the storage guys also says, you know what, it's a plug and play, right? It doesn't depend on motherboard. However, the management and CPU is still tied together today. And that's what DCSCM says, you know what, if I have the CPU spun up with a new CPU, Intel come out, or AMD or ARM or whoever it is, why do I have to, rest of the system, which is a management, control, security, why do I have to spun up for those, right? So why can't you make a card-based, modular-based, and that's exactly what the DCSCM is, right? DCSCM basically took the 3 functions out from the server, which is management, security, and protocol, and left the CPU alone. So if someone has a CPU, needs new CPU, they can simply spun up, and they can use the existing, security module, or existing DCSCM module to plug it in. That's the whole idea here is. And also it fits well because security doesn't depend on CPU generation, right? Again, security is something totally whatever hackers are doing, right? It depends on them. So it fits the very well the module, and that's where the DCSCM come out, right? So if you look at the DCSCM, so there's some benefits, obviously. It has, it changes the memory, security, and all those things. But it improves the platform design and validation because platform is a simpler design now. It's still complicated, by the way. I'm not saying that, but you are separating some of the big functions out of the CPUs, right? So it's a simpler platform design. It definitely improves serviceability because you don't have to attack the whole motherboard to solve a security problem or solve a management problem. You can individualize these problems, right? Definitely platform interoperability. That means if I have a DCSCM module, technically it should work for ARM servers or AMD servers or CPU servers. So that gives some flexibility today that you have all this, the problem we have, right? Getting the components. This could be helpful for that. And then it reduces the risk, obviously recycling the servers. The big thing is that, I think this is a big thing because if you have the security on a different card, right, when you recycle the servers, then all the keys and everything that you can recycle separately. That's a big importance things, right? So you can recycle the servers without a problem that, what, I'm giving the key away to someone else, right? So that's one of the big problems, fix that they're doing. And then it's a easier deployment of security management, and definitely DCSCM says, what, we need to have open source. So if you look at the DCSCM, as you mentioned, right, there's 3 things that are mentioned, which is what I think we are proposing that, you have a management, you have a security, and you have a control functions. And what happens is that management is pretty much done by the BMC, right, today. And then, BMC has, there's a lot of functions they do, right? But then, and the DCSCM board, they also have a security module, which is supposed to do the PFR functions or any kind of, non-PFR, if you just do, AMD doesn't have the PFR equivalent, just a PFR equivalent, right? And then the control, the way they implemented this control is just a programmable, it's a new interface that was introduced in DCSCM 2.0, which is LTPI, which basically moves the data between, because you have to wait to talk to the HBM or processor module side from the SCM side. And that's what Intel was heading that one, is they did a fantastic job on that. And that's an LTPI spec, right, that they developed, is already out there. And I can see Casper here too, who is the project lead on that. But yeah, that's what the whole LTPI interaction is, right? So if you look at, we can actually, we can actually look at this way, right? So we have the security, we have a LTPI. Why can't you combine these two together to a single chip? If it is an FPGA, we can certainly do that, right? And to a certain extent, I would even challenge more that even the system management can be served from a BMC perspective. Now, I'm not telling it's feasible today. This is something that's where the BMC is not some easy task to take. But I'm saying that it can be combined. It can be much more simpler design, right? You don't need everything like the way it is. Definitely security, and we have the capability today to combine the security and the LTPI together. And we have, one of our demo that we showed in our floor actually showing that LTPI 1.0 spec plus the PFR I2C monitoring that's doing.
One other thing. So also on the DCSCM card, as Munir's talking about, there is a security module, and many designs today that is an add-on module that's going on the card, and it does not get defined in the DCSCM specification, the pinout of that additional add-on module. So if we can work together as a community to drive a commonality of that connector, we can get a lot of advantages that we'll talk about in a moment.
Right. Thank you, Jake. Yeah. So I think the big thing here is, look, if we look at, So with the security, you can actually look, you can do pre-boot condition. You can validate all those things. And since the control mechanism is done by a single FPGA, right, you can do that. Once it is powered up, you can do constant monitoring all the flashes, all the BIOS or BMC, or any privilege firmware that you want to monitor. You can also introduce the attestation if you want to do that. If you want to have harder root of trust and fixed on something, you can certainly do that. And you can also do like snoop on the buses, which is possible because FPGA has a parallel nature. So if someone issues a command that can delete the flashes or do some harm, you can actually snoop on that. So that's the whole idea here, is that FPGA as and because FPGA already is serving the power sequencing, that's a big one, right? That means that I'm holding the sub-platform on when I'm only one who's allowing the platform to boot up, right? So that, why don't you also security root of trust? You need the security root of trust to be the very beginning. You cannot put a security root of trust like TPM, which is after the boot event. Well, it can have some functionality, but you know what? You are out of luck if something is bad. You have to have manual intervention on the servers to go there, right? So you want something in the beginning, to boot up from, and that you know that, right? So that's the distinction between TPM and harder root of trust that we're proposing. So the next slide is call of action. So,
yeah,
please.
So if we flip over to the call of action, it's a widely adopted standard, or DCSCM is within OCP, but we need some community enhancements. Do you want to talk about the first one?
Sure. So basically, I think we're saying that today, the DCSCM actually shows security as an optional module, and we're requesting that, with the way that we are seeing security hacks all over the world, and the way we're seeing that increasing number of security risk, and also that's a lot of dollar amount the company is losing because security is, we're requesting OCP to combine the security function, make it not an optional, make it at least in some form. I'm not saying the full PFR implementation, but at least the NIST compliance, that's a guideline. Let's make it some form of that not an optional anymore, right? Something that is required for the system perspective, right? And that something has to be driven by somebody from OCP side, right? We cannot do it our side, but I think we need to understand that security is a big threat for all of us, right? Yep. Definitely standardization is that we need to have a common connector there. So that means if we have multiple of these server vendors, we need to have some kind of way to do the common connector there so that it improves the operability. And then
basically, if we work on that common connector as a group, you can post-production add a hardware root of trust module so that it doesn't increase the overall cost of your server unless somebody's actually looking to make use of that. And if we can define that connector, there's obviously specific pins that it needs to talk to the different SPI chips, to do some power sequencing and everything like that. Then we can, in fact, extend that to other motherboards that aren't DCSCM. So you can get a lot of advantages if we can standardize on a hardware root of trust or platform root of trust like connector for the server space and beyond. It could be in desktop platforms, could be in embedded platforms, anywhere that people want to apply this. Obviously, this is going to take a lot of community approach. Not one proposed connector is going to be accepted by everybody, so we're going to have to work together on that. And we want to talk about also, we did some open source projects, so you can take a look behind this. Cerberus was obviously one of the first ones seeded by Microsoft several years ago, and then we just recently added our Tectagon Open Edition, our firmware for hardware root of trust or platform root of trust in the OCP repo. You can take a look at those, get an idea for how it functions. It has a full capable stack. There was a presentation on it earlier today, so I can't ask you to go attend it now, but please feel free to go and review it later and get involved in the projects, right? There's the security team, which is obviously spearheading a lot of the security aspects, and we're in this group, the hardware management module or hardware management sub-team to talk about how this applies to a lot of the hardware designs on the platforms.
So with that, I think this is the presentation, conclusion of the presentation. So please feel, if there is any question that we can take, please.
Yeah, thanks, Munir and Zach. Any questions? There are 2 mics here. If you have questions, come to the mic.
I have a disclosure to make. We have a root of trust which is embedded within our BMC. how do you handle update of the FPGA? One of the advantages of the FPGA is you can actually update it. But from security point of view, it's just another thing that you have to protect on the way. And the second question I have is, how do you maintain your secrets? How do you overcome the problem of not having real fuses or anything similar to that?
So I think there's a lot of things that still needs to be think through. You're right, right? The region that I want to work with the BMC, because if you look at the server perspective, you have a lot of peripherals, right? You have NIC cards, you have fans, you have power supplies, all those things, right? If you look at the existing infrastructure the server has, only BMC has a hook to all these peripherals. Nobody else has, right? And that's the big, problem from root of trust to work at a station and all those other devices if you want to do the, authentication of all the other devices. So initial proposal that I'm working on that we can go through, work through the BMC to the bridge, and still hard a root of trust at the separate. But end of the day, to your point, I think we need to still think through how we're going to do it. There is a possibility that we can have side-by-side operation running from single FPGA, basically partition that. That's a possibility, definitely. So root of trust will be, even though it's a single chip, it's going to work as like a chiplet interconnect, right? Multiple chips in a single chip piece. That's a possibility there. But truly, we need to have a way to BMC combine together, because that's the BMC has the only hook, unless someone goes to completely redesign everything else, right? Which is not going to happen soon, but we are trying to go through the BMC. That's what the main security that we're trying to achieve.
But still, you want to update your FPGA. There's data that has to come from somewhere, whether a flash or a network or anything, and you need to authenticate, and you need to make sure that we're worried about firmware being corrupted or harmed in some way. Now you add the hardware. You're adding a risk. How do you protect your update of the FPGA, which is definitely the most?
So the way that we do it today in FPGA, right? We pretty much put this golden image of the module inside the hardware, and it's a very authenticated. It's a very secret area that we do it, and then for example, if you are the customer, right? We give you a. It's not a public key, but we say it's a public key. So it's a private key. The thing that we do is that there is no way you can recover the key from the FPGA. It cannot be read-in, and it cannot be read, it cannot be get out. So that's the root of trust is there, right? And then we give this another part of the key that only customer can hold, and only they can unlock, some devices, right? So that's one way we do it. And I know there is some, some more improvement needs to be done, but that is something that we have today, which works,
There is a secure method of
solves the
updating.
problem.
Right. There is a secure method of updating as well. You have to
That's
make
your
the key.
fuses, basically. That's what you use for keys maintenance.
Right. The key actually, the matches, and then if you want to update something, you need to have this proper key there.
I guess I would say in many cases it's not a complete FPGA. There are some hardened portions of it that are more.
Correct. The hardened portion is I think this is a good point. So there is a hardened portion that nobody can read within the FPGA that we don't, nobody can actually read it. It's that's the harder root of trust is coming from, right? That's what all the keys are holding there. Okay.
Okay, I have one more question, and then we'll.
Okay, I was going to ask, so you talked about DCSCM, you focus more on that, right, where the value of the FPGA is as a hardware root of trust. So that, threat landscape that you're trying to protect is primarily biased in BMC, right? Now we talk about some of the I/O, we talk about, some of the other components on the system. Could you just shed a little more insight, let's say specifically for NICs, which have their own, secure boot mechanism in some respects? PSUs, you briefly touched on that.
Yeah.
PSUs today we know are not secure. There's efforts, by different vendors to try and build some security profile on them. But when we look at some of these other components in the system and we know that they're, to some extent vulnerable, where do you see the FPGA playing a part in that? A lot of these are connected through the BMC, right?
Correct.
Yeah.
Yes.
BMC could potentially be, a single failure point.
Agreed.
Right? Which means everything downstream doesn't matter at that point, right? So how do you see, us increasing the profile as an industry for the other components, be it component attestation, be it, an extension of what the FPGA could do more so than what the BMC does today.
No, you're absolutely right. The FPGA has a lot more flexibility in that the I/O isn't necessarily defined for it. So you can use additional pins or upgrade to a higher end FPGA to do additional monitoring and other things for these additional components. We'd also want to leverage SPDM and other technology or other standards out there to do better attestation. Of course, you could do bit banging and hashing and reading for people who don't want to follow standards. But the better way is there's some inherent security they'll build into their side, and that you can validate that it's properly responding to nonces on the other side and everything like that.
Yeah.
I think we are running out of time. If you guys can take it offline. I'm just being signaled. So let's have other questions.
I will talk to you. Yeah, sure.
Okay, let's thank our speakers.